Hi everyone, welcome back to this video series on cryptocurrency. Creating an HD wallet from the seed. HD wallets are created from a single root seed, which is a 128, 256 or 512-bit random number. Most commonly, this seed is generated from a mnemonic as detailed in the previous section. Every key in the HD wallet is deterministically derived from this root seed, which makes it possible to recreate the entire HD wallet from that seed in any compatible HD wallet. This makes it easy to backup, restore, export and import HD wallets containing thousands or even millions of keys by simply transferring only the mnemonic that the root seed is derived from. The process of creating the master keys and the master chain code from an HD wallet is shown in figure 5.9. So you can see here: cryptographically secure the pseudo random number generator, mnemonic, code words, army van, defense, root seed 128, 256, 512 bits, MAC SHA 512 bits output, one-way hash function, left 256 bits, private key M256 bits, master key M264 bits, master chain code 256 bits. The root seed is input into the HMAC SHA 512 algorithm, and the resulting hash is used to create a master private key M and a master chain code C. The master private key M then generates a corresponding master public key M using the normal elliptic curve multiplication process M star G. The chain code C is used to introduce entropy in the function that creates child keys from parent keys, as we'll see in the next section. Private child key derivation. HD wallets use a child key derivation CKD function to derive child keys from parent keys. The child key derivation functions are based on a one-way hash function that combines a parent private or public key, ECDSA uncompressed key, a seed called a chain code 256 bits, and index number 32 bits. The chain code is used to introduce deterministic random data to the process, so that knowing the index and a child key is not sufficient to derive other child keys. Knowing a child key does not make it possible to find its siblings unless you also have the chain code. The initial chain code seed at the root of the tree is made from the seed, while subsequent child chain codes are derived from each parent chain code. These three items, parent key, chain key and index, are combined and hashed to generate children keys as follows. The parent public key, chain code and the index number are combined and hashed with the HMAC SHA 512 algorithm to produce a 512-bit hash. This 512-bit hash is split into two 256-bit halves. The right half, 256 bits of the hash output, become the chain code for the child. The left half, 256 bits of the hash, are added to the private key to produce the child private key. In figure 5.10 we see this illustrated with the index set to 0 to produce the 0 first by index child of the parent. So see here, private key 256 bits, parent public key 264 bits, parent chain code 256 bits, index number 232 bits, e.g. 0, HMAC SHA 512 bits, output one-way hash function, left bits, child index 0, private key 256 bits, child public key 264 bits, child index 0, chain code 256 bits. Changing the index allows us to extend the parent and create the other children in the sequence, e.g. child 0, child 1, child 2, etc. Each parent key can have 2, 147, 483, 647, 231 children. 231 is half of the entire 232 range value available, because the other half is reserved for a special type of derivation we will talk about later in this chapter. Repeating the process one level down the tree, each child can in turn become a parent and create its own children in an infinite number of generations using derived child keys. Child private keys are indistinguishable from non-deterministic random keys because the derivation function is a one-way function. The child key cannot be used to find the parent key. The child key also cannot be used to find any siblings. If you have the nth child, nth child, you cannot find its siblings, such as n-1 child or the n+1 child or any other children that are part of the sequence. Only the parent key and chain code can derive all the children. Without the child chain code, the child key cannot be used to derive any grandchildren either. You need both the child private key and the child chain code to start a new branch and derive grandchildren. So what can the child private key be used for on its own? It can be used to make a public key and a Bitcoin address. Then it can be used to sign transactions, to spend anything paid to that address. Extended keys. As we saw earlier, the key derivation function can be used to create children at any level of the tree based on the tree inputs, a key, a chain code, and the index of the desired child. The two essential ingredients are the key and chain code, and combined these are called an extended key. The term extended key could also be thought of as extensible key because such a key can be used to derive children. Extended keys are stored and represented simply as the concatenation of the 256-bit key and 256-bit chain code into a 512-bit sequence. There are two types of extended keys. An extended private key is the combination of a private key and the chain code and can be used to derive child private keys and from there child public keys. An extended public key is a public key and chain code which can be used to create child public keys, public only, as described in generating a public key. Think of an extended key as the root of a branch in the tree structure of the HD wallet. With the root of the branch, you can derive the rest of the branch. The extended private key can create a complete branch, whereas the extended public key can only create a branch of public keys. Extended keys are encoded using base 58 check to easily export and import between different BIP32 compatible wallets. The base 58 check coding for extended wallets for extended keys use a special version number that result in the prefix XPRV and XPUB when encoded in base 58 characters to make them easily recognizable. Because the extended key is 512 or 513 bits, it is also much longer than other base 58 check encoding strings we have seen previously. Here's an example of an extended private key encoded in base 58 check. So I'm not going to read all this out because there's just too many numbers and letters. And here's the corresponding extended public key encoded in the base 58 check. Again, I'm not going to read all that. I'll just leave it on the screen there so you can have a quick look at it. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing, and give me a thumbs up. Thank you.